In this video, we're going to examine a few ways that we measure pressure, and we're going to try to get some intuition about how we can use it to solve problems and a little bit more about what it means. So, first thing to say is we've got to talk about the difference between two different types of pressure. Is not the right word to say. I don't like types, but two different ways to express pressure maybe is a better idea. We have what's called the absolute pressure, and we have what's called the gauge pressure. So the word gauge might invite what we're talking about here. If you measure pressure, and if you've ever, put a pressure gauge on one of your tires or filled up one of your tires with one of those air hoses that has a little thing that sticks out at the end to show you what the pressure is, or if you've ever read the pressure off a propane tank or something like that, you've used a pressure gauge. And so let's talk about what this means, and that leads us to some intuition about the difference between these two. Let's imagine that we have some sort of compressed air cylinder. Normally they kind of look like that. It's a little valve, and they've got some place to hook up a hose for your application. This could be propane to run a gas grill. It could be, oxygen if you're a scuba diver, or oxygen-nitrogen mix, whatever it is. And we know that outside is atmospheric pressure, which we call P0. And inside is some P, and if this is pressurized, then the pressure inside is a lot bigger than the atmospheric pressure. Now, let's open the valve and let all of this air out. So basically, we're opening the inside to the outside. There's going to be a difference of pressure. Pressure is going to want to equalize, and so all of the stuff that is inside the tank is going to get out of the tank until the pressures equalize. So inside, after I do this, inside, I've got P0, and outside I've got P0. I've got atmospheric pressure in both places. Now, assume I attach a gauge to this thing. What is it going to read? Well, you might say, well, it reads the pressure inside here, so it's going to read atmospheric pressure. And that might be the case, but that doesn't seem to do us as humans a lot of good. We expect atmospheric pressure. That's the pressure at which we live our lives. It's what our bodies are used to. And so it seems to make a lot more sense if I calibrate this particular gauge to read 0 if there is nothing inside the bottle. Right? That's what we want to gauge. We want to know the pressure of this stuff inside the bottle. If I let all of that stuff out to where I've just got atmosphere inside here, from a practical standpoint, I don't have a reason to know what the pressure is in there. So I typically calibrate my gauges, which I can do mechanically, to read 0 if the pressure inside is atmospheric, right? Because I expect atmospheric pressure. What I'm reading is then called the gauge pressure. But you might argue successfully, but there is stuff inside the bottle. It's just atmosphere. And there is a pressure inside the bottle, just like there's a pressure outside the bottle. It's atmospheric pressure. And you would be right. And so if that's your stance, you might be more interested in what's called the absolute pressure. And in this case, the absolute pressure would be atmosphere. That is absolutely what it is. But the gauge pressure, the pressure that you're probably going to want if you're reading a gauge, is 0. So, what can I say about that? Well, I can probably do this. The absolute pressure has got to equal the gauge pressure plus the atmospheric pressure. You see what I'm doing? If I'm doing a practical application, the gauge pressure is probably what I care about. If I'm filling up a cylinder with acetylene, I'm going to do some plasma cutting or something like that. What I care about is how much stuff is in the bottle, and that's the gauge pressure is going to give me. If I'm doing some sort of structural analysis of the strength of the body of this, I might care about the absolute pressure. To do that, I need to recognize that I'm always going to have, as long as I'm open to the atmosphere, I'm always going to have this additional term, atmospheric pressure, so I can then talk about the absolute pressure as the summation of both of those. So it's actually a pretty simple way to approach it. If you want the absolute pressure, you add atmospheric pressure to the gauge, to whatever the gauge reads. If you just want gauge pressure, you just read that. It's not a big deal. So that is what we mean by absolute pressure and gauge pressure. The difference between them is the atmospheric pressure, which we usually, how you encounter it in this country is about 14.7 pounds per square inch. That's obviously not an SI unit, but that's usually, if you encounter that in real life, you normally encounter atmospheric pressure. It's 14.7 PSI, pounds per square inch. All right, so that still leaves the question of how do we measure the gauge pressure? That's actually a really interesting physics problem. So let me introduce you to something called a manometer. A manometer, it looks like manometer, but it's manometer, is just a tube. In this case, in all cases, it's going to be open here at the end. So this is open and open. Now, I say it's open. I might connect one side of this to something, but what I'm saying is there is an actual opening of the tube. That opening might go into another chamber, but this is just a tube that's open at both ends. And I'm going to put some sort of fluid in there. This fluid will have some sort of density rho. That's the density of the fluid that I put in there. And if both sides are open to the atmosphere, it's probably not a surprise that this is what's going to happen. The level on both sides of these is going to be equal. So it seems like I haven't done a whole lot yet, and I haven't. But if I then take this system and I connect one side of it to something else, let's connect it to some sort of system that is pressurized. Your book uses the example of a balloon, and that's good enough for me. We're all familiar with that, with balloons, and that they have pressure, right? We have to blow them up, and the rubber of the balloon squeezes that air and pressurizes it. Well, in this case, the pressure inside the balloon is going to be greater than atmospheric pressure, right? That's why the balloon is pressing down, or is squeezing the air in the first place, because the air pressure outside is pushing in on it. So the pressure inside this balloon is greater than the pressure outside. So what's that going to do to the fluid? Well, pressure, remember, is a force per unit area. So that's going to exert a force on this face of the fluid that pushes it down. So I'm going to find that this side of the fluid has been pushed down. How far does it push down? Well, it pushes it down until it comes into equilibrium, right? There's also a force on this face of the fluid from the atmosphere. So by attaching this balloon, I now have a force here. I have a force down there that is going to have to balance with the force down here. This force is from the atmosphere. This force is from the pressure inside here. Let us assume that the areas of these, the cross-sectional area of my tube is equal. It doesn't have to be, but let's assume that it is. Let me go across, and so I'm going to hatch the fluid thusly. I'm going to cross-hatch that section of the fluid which is above the level over here. Okay, so if I just do some Newton's second law here, I've got this volume of fluid whose weight is pushing down upon this, and that is going to have to balance with the force upwards on this little line right here. This is not an actual structural line. I'm just showing you where the level is. But everything above here, we know it wants to come down. But this pressure, this force that's on this side is pushing the fluid in the U-turn here up. And so I'm going to have to balance the forces at that point as well. All right, I know if I draw a free body diagram on this particular section, I've got mg. I've got mg down, but I'm not going to write it as mg. I'm going to write it as rho VG. Remember, rho V from the definition of density, mass per unit volume. Rho times V is a mass. And so I'm writing mg, I'm going to write rho VG. The force that is balancing that, if this is truly in equilibrium, has got to equal rho VG. Right? If this is in equilibrium, this force has to balance this force. Where does this force come from? Well, it is transmitted through the fluid from over here. So that has got to be the force acting down on this surface to push this amount of fluid up above that level. So now I can say that this force is rho VG. Okay, that still doesn't really tell me pressure, but if I then rewrite this a little bit, rho VG, the volume here, what if I write the volume as this height h times the area of that bottom surface? This is then equal to rho AHG, where AH is my volume. I've assumed that the area over here is the same as the area over here. So this is the force. That means if I take that force, rho VG, and divide it by the area of that face, I get the pressure, right? Pressure is, that's density. Pressure is force per unit area. So rho VG I've determined is the force. Let's divide that by the area of this little cross-sectional surface, which I said is the same as this. And now let me rewrite rho VG as what I wrote it over here. Equals rho AHG over A. Because I was careful to keep my A's the same, I get rho, let me rewrite it in the way with which we're familiar, rho GH. So that is the pressure acting on this surface, which means that's the pressure everywhere in it. We're going to ignore any slight changes due to the height of this. They might be there, but we're going to assume that they're small enough to be negligible. So that's the pressure I find here, which means that's the pressure I find all through this system. So that is a manometer. It also works the other way, I should say. If this is not a balloon, if this is some sort of evacuated cylinder, I'm going to find the opposite effect. The pressure over here will be lower than atmospheric pressure, and this column will be pushed up. It will be pushed up from the outside. The same reasoning is going to get me the pressure inside is negative rho GH. So if the pressure here is less than atmospheric pressure, I'm going to register it as negative. That is a gauge pressure. This is how I measure gauge pressure. So if the pressure here is greater than atmospheric pressure, I register it as a positive rho GH. If it's less than atmospheric pressure, the column goes the other way. I register it as negative rho GH, not R, negative rho GH. So atmospheric pressure here is serving like some sort of zero, like a baseline. So anything less than atmospheric pressure, I gauge it as negative. Anything greater than atmospheric pressure, I gauge it as positive. This is a manometer. The cuffs that they put around your arm when you go to the doctor to measure your blood pressure work somewhat like they're called sphygmomanometers. You can look into that if you're interested, but they work somewhat like this. They use changes in pressure in that cuff to register and then against a baseline to determine the pressure in your blood. So that's a manometer. There's another way to do it. Another way to measure pressure, which if you ever watch the Weather Channel or the news or the weather on the nightly news, you have seen or heard about barometric pressure. Another way you can measure pressure is with a barometer. A barometer works similarly to a manometer. In this case, though, we construct a system such that I evacuate a tube. And by evacuate, I mean I create as good a vacuum as I can possibly get. And then I immerse the open side of that tube. I invert the tube and immerse the open side in a liquid. As it turns out, mercury is a really good candidate for this. Mercury is an incredibly dense substance, which means just a little bit of mercury weighs a whole lot. That has the advantage here of meaning that I don't have to construct a tube that's 6 stories tall, like I might have to do if I was putting water in here. Mercury actually makes this really easy to measure. But we're going to say that in this thing is mercury, and I put a vacuum in the tube, and then I inverted it in mercury. What is going to happen? Well, the pressure here inside the tube is nothing. There's a vacuum. It's not open to the atmosphere. So I get actually nothing there, which means I get from the outside, out here of course is atmospheric pressure, which means there's a force being exerted on the surface of this mercury from the atmosphere. That then pushes some of the mercury up the column, right? And so I'm gonna hatch where the mercury is. So I have mercury that's been pushed up the column. That's advantageous to me because I can then just actually measure this, right? I can measure the height of the column of mercury, that's some h. And if I know exactly what I'm using for a reference, right? This 14.7 pounds per square inch, if you're here in the States, for atmospheric pressure, then once I do this, and if I'm sitting here at exactly what I take atmospheric pressure to be, I can put a little mark here and construct a scale on this. And so I know at atmospheric pressure, this is at a certain height. Now, atmospheric pressure varies, right? This is a constant. I take this as a baseline, but the actual atmospheric pressure, whatever it is at this moment, varies around this number, right? This is, you can think of it kind of as an average value. But the actual pressure varies. It drops when there's going to be a thunderstorm. It increases on a really hot, humid day. So it varies as part of with your altitude and the weather. So the reason we care about barometric pressure is the fact that it does change. So what happens? Well, imagine, if you will, the atmospheric pressure outside this thing goes down. Well, what that means for these forces that are exerted on the surface of this is that they decrease. The area hasn't changed, of course. Remember, pressure is force per unit area. So if the pressure decreases, the area of this liquid, the surface of this liquid open to the atmosphere, hasn't decreased. What had to have happened was the force goes down. So these forces don't push down quite so much, which means this column falls. The reason this column is high is because these things are pushing down and pushing it up. And of course, you can run the Newton's second law analysis here. The net force on this surface has to equal mgh, where mg, where m is the mass of the mercury inside this column. You could then turn that into a rho gh if you're clever about it. But if these forces go down, the column falls. And if I know my baseline, and I know how much it falls, I can then calculate the new pressure. In point of fact, we usually just give you the pressure in inches of mercury, or in millimeters of mercury. If the pressure increases, of course, that means these forces get bigger and the column rises a little bit. Again, mercury is very dense, very heavy. So if the column is thin enough, I don't need to move this very much. And in fact, it's hard to move it very much because the forces can't vary that much because this is so dense. But if I make my column narrow enough, I can see how it moves pretty well. So if you ever read a barometric pressure reading of millimeters in mercury, inches in mercury, that's what this comes from. This is a barometer. They're usually constructed a little bit more securely than this, right? We don't want mercury just kind of sitting here open to the atmosphere and able to spill out. But in essence, this is a barometer. Anything past this basic design is just safety and structure, but this is a barometer, and this is how we measure pressure. This is how we measure current, instantaneous pressure in the atmosphere. We use this P naught as our baseline, and we can measure it using this particular apparatus.